Multivariable Calculus, Section 13.2, Volumes over General Regions. Review. Volume bounded by a rectangular region is what we've done in the previous section. And what we did was we just integrated along the x-axis from A to B and then along the y-axis from C to D, or in the other order. And we looked at a Riemann sum of the z-values over the areas, and the area was always rectangular. So now we're going to look at what we need to do if the region below the surface under which we're computing volume is not a simple rectangular region parallel to the x and y axes. Volume bounded below by a non-rectangular region. So for example, here we have a quarter circular region, and as we move from the left to the right, the little squares get smaller, and so the change in x and the change in y get smaller and smaller. Now the volume then is up above this region, and so you could imagine rectangular solids being used to approximate the volume, and these rectangular solids get smaller and thinner and thinner as you move to the right, and therefore your approximation for the volume would get better and better. And so the volume of each of these rectangular solids would be the particular z value we're using somewhere in that area times the change in y and change in x. That was how you would get the volume of each little rectangular solid that's approximating the actual volume. Now, as delta x and delta y get smaller and smaller and go to 0, they change into the instantaneous changes, dx, dy, and then the volume becomes exact, and it's the limit of the sum of the individual rectangular solids as n goes to infinity. The number of them goes to infinity, then the change in x and change in y will also go to 0 and change into dy dx, and so the actual volume will be the double integral z dx dy. Okay, so what's new here is that x does not always move from 0 to 1. If y is a small value, x moves further than if y is a larger value. So what is true is that x does always move from 0 to the curve, regardless of what the y value is. So now let's look at a particular example. For example, let's say our z value is always x plus y, and then we're going to need the equation of the curve so that x can move from 0 to the curve, and there's the equation of the circle with radius 1. Now, because we're integrating with respect to x first, we have to go from 0 to the curve, okay? And the curve is not at a particular number, so we're going to have variable limits, okay? And then we'll integrate with respect to y from 0 to 1 to cover the entire region. So here's our integral. We're going to integrate our function x plus y. We're going to do it with respect to x first, and x is going to go then from 0 up to the right and hit the curve, which is, if you solve for a positive x value, you get the square root of 1 minus y squared. So x is going from 0 to the square root of 1 minus y squared. And then after we integrate with respect to x, we'll integrate with respect to y from 0 to 1. So with respect to x, our antiderivative is a half x squared plus xy, because y is treated as though it were a constant. It's not ignored, it's just treated as a constant. And then we substitute our two limits, and when we put 0 in for x, both terms will be 0. So we just end up substituting basically the square root of 1 minus y squared, and we get kind of a nasty integrand. So once you get it to a single integral, if the algebra and the calculus is going to be annoying and complicated, feel free to use your calculator. However, I went ahead and did this. The first two terms are easy, of course, and then the last one I sort of did use substitution in my head. And then finally I substituted the 1 and the 0 and got an answer of 2/3. Now, because this particular region is symmetric, we could integrate with respect to y first. So this time we're going to integrate from 0 up to the curve along the y-axis, and then we're going to integrate from 0 to 1 along the x-axis. So our integral is similar, except it's dy dx instead of dx dy. And this time for our upper limit there, we solve for y on the boundary, so y equals the square root of 1 minus x squared. Now going through the calculation rather quickly, we're integrating with respect to y, so we get xy plus a half y squared. We substitute our limits in terms of x, and again we have a messy integrand, so if you would prefer to use your calculator, go ahead. I did it by hand. The first term I used u substitution, did it in my head. Second two terms are easy to integrate, and then we substitute our 1 and our 0 and get the same answer of 2/3. Now later though, we're going to have regions that are not symmetric, and so one of our problems is going to be to decide whether or not to integrate with respect to x first or to integrate with respect to y first. And that involves deciding what type of region we have, and that concept is called simple regions. So let's look at simple regions next. Volume bounded below by a simple region. Now we're only going to be able to do these for simple regions. We have to define what does that mean. Here is a region that is vertically simple, because if you move vertically you go from one boundary curve to another boundary curve. And so we would integrate along the y-axis from those two functions in terms of x, and then everything would be in terms of x, and we could integrate from a to b along the x-axis secondly. Okay, this region is horizontally simple because we can move horizontally from one curve to the other and integrate parallel to the x-axis first. So that integral we would go from x1 to x2, integrating the function whatever z happened to be along the x-axis, and then everything would be in terms of y. So then when we integrate the second time in terms of y, we can integrate from c to d along the y-axis. Now this one is vertically and horizontally simple, because as shown we can move from curve to curve vertically, but with the same region we could also move from curve to curve horizontally. And so you have a choice in this case. You can integrate with respect to x or y first, whichever is more convenient. Now some students have trouble with this vertically simple, horizontally simple concept. So here's some more examples. In the first area, the gray area, think of a vertical line going all the way across the region. And because that vertical line always spans through the region from G at the bottom to F at the top, then that region is vertically simple. Now the red one. This time when you get over to the right, the vertical line passes through the region, then out of the region, and then through the region again. That means it's not vertically simple. It has to always stay in the region and go from one function, or one curve rather, to the next. Then the purple one, the problem with the purple one is it's going from the same curve up to the same curve, and so that is not vertically simple either. It has to be bounded by two different curves. Now I suppose you could rewrite f in terms of two separate functions or two separate curves and then work it that way, but technically this region is not vertically simple. And then the aqua shaded one is vertically simple, even though the boundaries are rather complicated functions. We're always passing from G at the bottom up through the region and then touching F at the top. So that region is also vertically simple. Now let's look at the same regions horizontally. Now we were okay until we got up to the top curve, and now horizontally you're passing from F to F. So even though you're staying within the region, you're not going from one function to another function, or rather from one curve to another. So that gray area is not horizontally simple. What about the pink-red region? Well, this time, all the way up and down, you are passing from F on the left to G on the right and staying inside the region. And so that region is horizontally simple. For the purple one, we're always traveling from F on the left to the vertical line on the right. So that one is horizontally simple. And then the last one, as we pass that horizontal line down through the region, we're going in and out. And so that region is not horizontally simple. Now let's look at some more and see if you can tell me which ones are horizontally simple and which ones are vertically simple. What about the red one? What do you say? Well, that's both. Imagine a vertical line passing will always go from G at the bottom to F at the top, and a horizontal line will always go from F at the left to G at the right. What about the blue one? Well, that's also both, because obviously a vertical line and a horizontal line stay within the region and pass from one boundary to the other. What about the green one? That one's neither, because sometimes you're going from F to G and H to K horizontally, and sometimes you're going from F to H, or rather from H up to F, or H up to G, and then K up to G. So you're always switching your curves, and so technically that's neither. And the same thing for the yellow one, because you're going to be going outside the region to the right, to the left, to the top, and to the bottom when you pass those lines across that region. Now the green one is a little bit interesting because you could do something with that. You could split it into 3 regions, and now each of those regions is vertically simple. So the green region can be split into 3 vertically or horizontally simple regions, because you could do the same thing with 2 horizontal lines, split it into 3 horizontally simple regions, and then do 3 problems basically instead of just 1. But it's, as a whole, it's not vertically nor horizontally simple. So here we have 2 curves, and in between them is a region. The black curve is y equal plus or minus the square root of x, or x equals y squared, and the red line is y equal negative x plus 2. Is this region vertically simple? Well, the right side is, but the left side is not. So no, this is not vertically simple. What about horizontally? Well, no matter where we draw our horizontal line segment, we are going from the black curve to the red curve, so yes, this region is horizontally simple. And so we would have to integrate with respect to x first and get the functions in terms of y, so that when we integrate with respect to x, everything ends up in terms of y, and then when we integrate in terms of y, we go from negative 2 to 1, because that's the y value varies from negative 2 to 1. And so whatever f of x, y is, that would be the z value, and that's what defines the height of the solid. Sometimes we have to split a region into several simple regions in order to work the problem. For example, here, region 1 is vertically simple, and region 2 is horizontally simple. And so you'd have to split the problem into 2 different problems, and for region 1 you would integrate with respect to y first, and for region 2 you would have to integrate with respect to x first. Here are problems number 2, 12, 20, and 30, worked live by me, Mrs. Cantey. Copies of each problem are in the PowerPoint at Google Docs. Okay, now before we get started, it's important that you have the right supplies. You have to have your book. You have to have plenty of paper, pencils, and erasers. You need to have something to drink, some chocolate, very, very important, and of course, a box of Kleenex in case you get teary-eyed. Ready to go? We're going to start off with number 2. evaluate the double integral from 0 to 2 and then from 0 to 2x of 1 plus y dy dx. So we're going to do this first. And we're integrating with respect to y. So we get the antiderivative of 1 is y. The antiderivative of y is 1/2 y squared. That's from 0 to 2x. And then we keep the x parts. 0 to 2 dx. Okay, so now we substitute 2x in for y, and 0 is just going to give us 0, so we can kind of skip that. We get 0 to 2, 2x plus 1/2 4x squared dx, which equals 0 to 2, 2x plus 2x squared dx. Simple, simple integral, x squared plus 2/3 x cubed, 0 to 2. Now it's just a regular integral like you've always done. And we put the 2 in, and the 0 is just going to be 0 again. So we get 4 plus, let's see, 2 cubed is 8 times 2 is 16/3, which is 12 plus 16/3. And so our final answer is 28/3. Ta-da! And now, the most important thing to do when you get done, eat a few little pieces of chocolate. Nom, nom. Nom, nom. Okay, moving on. Nice brush, clean piece of paper. I'm going to do number 12. Number 12, we have 0 to pi, 0 to sine x, y dy dx. So again, we're starting out with an integral that's in terms of y. So we're going to get 0 to pi, 1/2 y squared from 0 to sine x dx. And that's going to equal, and put the 1/2 out here, 0 to pi, 1/2 sine squared x. And again, if I put 0 and I get 0, so it's minus 0, so I'll just skip that. But be careful, they might trick you. It won't always be 0. Now, this one, to integrate, oh, I did the half twice, didn't I? Oopsie, that's a danger doing this live. The half's out here. Now, this one we have to change using an identity. It's standard procedure when you have a square that you use this identity. 1/2 minus 1/2 cosine 2x dx. Now I'm going to take that half out. 1/4, 0 to pi, 1 minus cosine 2x dx. So that's going to be 1/4 x minus, now you get a backwards baby here, so that's 1/2. Now wait a minute, the antiderivative of cosine is positive sign because the derivative is negative sign. So we keep that one. And that's from 0 to pi. Okay, so now if I put pi in, I get 1/4 pi minus 1/2 sine of 2 pi. And again, if I put 0 in, I'm going to get 0. But it won't always be that way. And this is 0. So I'm just getting pi over 4. Ta-da. And what's the most important thing to do next? Yes, eat some chocolate. Okay. Moving on. Okay, now we're going to do number 20, which says that f of xy is sine x, and the region is going to be bounded by the x-axis, the curve y equal cosine x, and we're going to keep x between negative pi over 2 and pi over 2. So you know me, I like a picture. Here's the xy plane, here's the x-axis, that's one boundary. And then we're going to keep x between negative pi over 2 and pi over 2. And then the cosine curve is going to look like that. And so this is our region right here. Now, which way should we integrate first? Should we integrate parallel the x-axis first? Well, that would be tricky. I guess you could change to arc cosine or something, but let's not do that. Instead, let's integrate parallel to the y-axis first. So we're going to start with sine x dy, and that's going to be from 0 up to the curve parallel to the y-axis, 0 to cosine x. And then we're going to let x go all the way across the region from negative pi over 2 to pi over 2, its values, all of its values. And then that's dx. So integrating this with respect to y, we treat this as a constant. So we just get y sine x from 0 to cosine x. Negative pi over 2 to pi over 2, keep the dx. Okay, we'll come over here. So now when we plug in the 0 for y, again, we're going to get 0. So we're just plugging in cosine x. That's all we need to keep. And let's see, so then we have cosine x sine x dx. Now, you could let u equal sine x and du equal cosine x, and then make sure you change the limits of integration, but I'm going to do this. I'm going to put a 2 there and a half there, because that's an identity that will make life easier, for me at least. That's going to be sine 2x dx. So now my integrand is easier. I get the 1/2 here. I get another 1/2 because of this 2. And then the antiderivative sign is negative cosine from negative pi over 2 to pi over 2. So we get negative 1/4 cosine pi minus negative 1/4 cosine negative pi. And that's going to come out to 1/4 minus 1/4. That's going to be 0. Okay, what's that all about? Well, come back up here. Your z value is sine x. So above, on this region right here, your z value is going to be positive. It's going to be up above the xy plane. But here, from 0 to negative pi over 2, sine x is negative. So you're going to have the surface below the xy plane. And both regions are going to be the same size. And so the positive volume above and the negative volume below canceled out and gave us 0 for the integral. What's the most important thing to do now? Yes, eat some chocolate. Yum yum. Okay, finally, number 30. Sketch the region reverse the order, tricky, and then evaluate. So they're giving us a double integral 0 to 1, y to 1, e to the negative x squared dx dy. Okay, now see, the problem here is you can't integrate that with respect to x. But if we switch, then we have to put the y values here, and they have to vary, and then the x values here, and they can be constant. So let's draw a picture. We've got, this is the z value right here. And x is going from y to 1. So we've got x equal y, and we've got x equal 1 to match this. So x equal y looks like that. And x equal 1, let's call this 1 right here so I can see what I'm doing. That's 1. And then y goes from 0 to 1, so that kind of makes sense because this would be 1, 1, wouldn't it? So here's the region. So if we switch and put e to the negative x squared dy, then y has to vary. So y is going to go from 0 to what? Well, this is y equal x. So y is going to go from 0 to x. It has to be x values here that we plug in because we're going to be integrating with respect to x next. So after we get through with this, everything has to be in terms of x. Okay, and then x is going to go from 0 to 1. Okay? So now integrating this with respect to y is just e to the negative x squared times y from 0 to x, which is going to be x e to negative x squared minus 0 again. Boy, they're making me nervous with all those minus zeros. So now we've got 0 to 1, x e to the negative x squared dx, and we can use substitution, let u equal negative x squared, du equals negative 2x dx, negative 1/2 du equals x dx, right? And so that takes care of that. with a negative 1/2 du. And then e to the negative x squared becomes e to the u. And then what do we get here? Negative 0 squared and negative 1 squared. And I don't like all these negatives, so let's switch it and go negative 1 to 0, which makes more sense anyway. E to the u du. And that's going to be 1/2 e to the u from negative 1 to 0. Finally, we're getting two numbers here. And so we get 1/2 e to the 0 minus 1/2 e to the negative 1, which is 1/2 minus 1 over 2e, right? And then the book likes you get a common denominator. So e minus 1 over 2e. And we're done. And we'll finish with a little more chocolate. Good stuff. And so now, here we have a video of how to build your very own Klein bottle. A Klein bottle is the 3D equivalent of a Mobius strip. So here you go. Take your piece of paper, or well, you'd have to have some flexible materials, wouldn't you? All right, after you build your Klein bottle, you can do some problems in section 13.2. Have fun.